What if we needed to scan a system, but we didn't want to get caught? Meaning, we don't want anybody to know exactly who was doing the scanning. Is that possible? The answer, my friend, is absolutely yes, using an idle scan. To better understand how an idle scan works, let's just do a quick review of basic TCP operations. If this client makes a TCP SYN request to this host on port 80, and if port 80 is open, the expected response is going to be what? What would we expect to get back from a host where web services are running? And if you're saying, Keith, it would be a SYNAC. You would be absolutely correct. And then based on what the attacker is doing, it could complete the three-way handshake or send a reset. But now the attacker knows that port 80 is open. Let's do another example. Let's say we send a TCP SYN request for port 80 to this second host. Let's call this host A, host B, and host C here. So we send a TCP SYN request on port 80 to host B. And if host B did not have port 80 open, what would we expect the response to go back from host B back to the attacker? What would that response look like? And if you're saying, Keith, it would be a reset, a TCP segment being set back with the reset flag set. If that's your answer, my friend, absolutely right on. So that's a quick review of basic TCP operations, but what additional information I'd like to bring to the table right now for you and I is that in IP version 4, there is a fragment identification number on each IPv4 packet. And you might say, well, Keith, why does that matter? How is the fragment ID number going to help us with an idle scan to do stealthy scans of the network? And the answer is we can take advantage of a zombie. We're going to use host C as our zombie. And let's say host C's IP address, let's put some IP addresses on here. Let's put 216 for host C. For host A, let's use .212. And for the attacker, let's use .109. What we could do is we could probe the zombie at .216 with a TCP SYNAC. And because we don't have an established TCP session with the zombie, we're going to get back a reset message saying, hey, you're crazy. And that reset is being sent because host C says, hey, I don't have a session with you. But what's included in that reset is there's also an ID number associated with the IP packet. So as an example, let's go ahead and associate an ID number of 337 with that reset packet that we got from host C. So that is step number one. Find and probe a zombie and glean from that the actual ID number of the packet that they sent back. For the second step, let's imagine that it's this machine right here, host A, that we want to learn more about. We want to scan host A. But we don't want the network to know that we're doing the scanning. So instead of sending a TCP SYN request from our own IP address, what the attacker is going to do, he's going to spoof the source address, and we're going to send a TCP SYN request from the source address of .216 with the destination of the IP address of host A, which is .212. So I've got another question for you. What does host A do if it has port 80 open and it receives a TCP SYN request from .216? What's the next logical step for host A? It's going to go ahead and respond back to .216 with a SYNAC. And that SYNAC, because it's going down to 216, is going to go right down here to host C. Now when host C gets that SYNAC and says, you know what, I don't have a conversation with you, host C is going to send a reset back up to host A. So the first packet from host A to C would be the SYNAC, and the second packet from host C to host A would be the reset. And let's presume for this example that host C is using incremental numbers for all of its IP packets. And if this is the very next packet it sent out, the first one was 337, this one would be 338. So that's step 2. Send spoof packets over to the intended scanning victim and allow that victim who's getting the scan to respond back to host C, our zombie, and have host C send its reset back to host A. And the question may come up, well, how is that going to help us? We don't even see that conversation. If it's a switched network, that SYNAC and reset is all going just between host A and host C. And the third step is the magical piece that makes it worthwhile. We're going to probe the zombie again. We're going to send another SYNAC over to our zombie and take a look at the response. And when the response comes back, if we get another reset, this time the reset, if it's using sequential numbering, would be 339. And presuming, and it's a little bit of a presumption, that we've picked a zombie that's not too busy doing anything else, we can deduce that because the current ID number we're seeing for the packet we're getting from host C is 2 greater than the initial one we saw, that it did the reset, which would imply that that port is open on host A. Now the question may come up, okay, what if the reset we got from the zombie on the second probe, what if it came back as 338? That would mean there was no interaction between host A and host C. which would be the case if host A either had that port closed or if it was filtered. And that's because if host A received a TCP SYN request for port 80 and the port was closed, it would simply send a reset down to host C, and host C is not going to follow up with any kind of acknowledgement for a reset out of the blue. And because it's not wasting a packet by sending anything up to host A, we can assume, based on the 338 number that we got, that the port is closed. So when we do that second probe of the zombie, if the ID has increased by 2, that's a good indicator that our victim machine, the target itself, has that port open. If it comes back incremented by 1, that would be indicative that the port on the target machine is closed, or at least filtered. So we're here on the Kali Linux box, and let's do a simple scan to find out what devices are out there on the network. And we'll use the command nmap-sn space, and then the subnet of 192.168.1.0/24. I just want to find very quickly what devices are out there on my network. So I've got 13 hosts that are up. So we'll do our stealth scan, and we'll scan the .212, and we'll use .216 as the zombie. So to do the scan, we're going to type in nmap space -pn. Now the dash capital P lowercase n simply says skip host discovery. If we want to do a stealth scan, we do not want to have direct interaction with the target. And that just helps us be a little bit more stealthy because we're not going to directly interact at all, even for host discovery, with our target, which is .212. Next, we're going to do -s for the type of scan and a capital I, which is for an idle scan. Next, we're going to specify who the zombie is that we're going to use. And we're going to use 192.168.1.216. I'll put a space, and then we're going to specify the target that we're trying to scan. And that's going to be 192.168.1.212. So we'll press enter to launch this. And let me pause the screen for just a second. So it's using the zombie at 192.168.1.216. That's perfect. It also indicates that on that platform, it's using incremental identification numbers, which is important for this zombie to work. And in less than 13 seconds, it's identified a whole bunch of ports that are open, which includes port 80 and a whole boatload of ports up in the 49,000 range. And I don't think that caught everything, so I'm going to go ahead and run that one more time. And that's more like what I was expecting. So it has 53, 80, 135, 139, 445, and then a whole boatload at the 49,000 range. And the cool thing about doing this type of a scan is that we didn't have to directly interact between our host at .109 and the server at .212. So if they're doing intrusion prevention systems or detection systems, the alarms that would be firing off would be scanning that's happening between .216, which is our zombie, and 212, which is the victim. In fact, if we want to see a little more detail of that, we could do that same command and just kick it up a notch. I'm going to add in a range of ports to scan. I'm going to say port 50, let's say 50 through 200. By default, it's going for 1,000 popular ports. It found these that were open and 987 that were closed out of the 1,000 it checked. And as you can see from the numbering, that's not 1,000 literally, but instead it's 1,000 ports that Nmap has identified as more likely to be open. So that's the 1,000 it's checking by default. Also here, we can add some additional output with -- packet trace. And that will visually show us additionally what's happening behind the scenes as the attack machine is sending the probes over to the zombie and also the spoofed SYN requests over to the target. So we'll press enter. And let me make the screen a little bit wider so we can see this. So within the range of ports that we just scanned, it's showing us these that are currently open. And we also have a play-by-play. So we have the attack machine at .109 talking to 216. And we have 216 talking to 109. But at no time did our attack machine at .109 have direct communications regarding this scan that we just did with the victim at .212. In this nugget, we did 3 basic things. Number 1, we introduced an idle scan. Secondly, we talked about how it worked. And third, we demonstrated it in action by using Nmap. I hope this has been informative for you, and I'd like to thank you for viewing.